Okay, in this video, we're going to talk about the concept of solubility equilibrium. And usually in chemistry, we assume for a strong electrolyte like sodium chloride that if you were putting this in water, it's going to completely dissociate. So single arrow to the right, not in equilibrium, it 100% completely dissolves into its ion sodium plus and chlorine minus. And that's true, but only as long as they actually dissolve that the sodium chloride molecule can fit in a space within the water. So there is a point where you can only add so much sodium chloride into water where it does break apart and ionize. And that turns out to be at room temperature about 359 grams per 1 liter of water. Okay, so you can pour some sodium chloride in water, stir the water, it dissolves and makes Na plus and Cl minus. But once you get to 359 grams into a liter of water, doesn't matter how much more you put in and how much you stir, simply no more than 359 grams is going to fit as ions. It's just going to clump up and sit as a precipitate at the bottom of the beaker or pot of water or whatever you're doing. So the sodium chloride no longer dissolves. And this 359 grams per liter is called the solubility. It is a particular amount for every kind of ionic compound that represents how much can dissolve in 1 liter. Okay, we also sometimes express this as a molar solubility. So if we're just saying solubility, it's kind of implied that it's grams per liter, but we can also have molar solubility. Let's just say it's 7 moles per liter or something. Okay, moles per liter or molarity is kind of how we express that molar solubility. And so both of these will tell you how much can fit in a saturated solution, right? That is the point of saturation, the maximum amount that can fit. Technically, we can achieve super saturation, but for all intents and purposes, like this is as much as it's going to fit, and that can be expressed in grams per liter or moles per liter. So now let's think about this sort of pictorially. And if we have some solution of water, and there's going to be some ions in solution. Let's say the sodiums are going to be little red spheres, and the chlorines are going to be little blue spheres, right? So some has precipitated out at the bottom of the container. Some is still floating around as ions. Okay, so these up here are the ones floating around as Na plus and Cl minus. These down here are precipitated out solid sodium chloride. And so if we think about Na plus and chlorine minus sort of approaching each other here, they can join up and make a solid sodium chloride that then sort of falls out of solution. But on average, there is going to be a certain number of ions floating up here, because every time two join up and drop out, somewhere else, a solid sodium chloride will fall apart and generate a sodium plus and a chlorine minus. So all I'm showing here is that this is a dynamic process. There is overall a certain amount that you can expect to float around in the solution and be ionized. Okay, that is the solubility. But this, what I'm hinting at, also corresponds to an equilibrium. So there is an equilibrium associated with this process. That at the point of saturation, when you've met this 359 grams per liter, okay, some ions will be forming up, and as they collide together and make a solid sodium chloride somewhere else, some are falling apart at an equal and opposite pace. And this is a dynamic equilibrium. Okay, so this is just reinforcing this concept of an equilibrium and a double arrow, but just applying it now to solubility, that this process can go both ways. It is happening at the same rate, equal and opposite, such that overall there is some on average number of ions up here at saturation that corresponds to this solubility. So this all hints that there is a equilibrium constant for this process, KEQ. And so this is solubility equilibrium. Ionic compounds are strong electrolytes and will dissociate completely to the extent that they dissolve. But at the saturation point, we can consider there being an equilibrium equation for this process, where the left side is going to be the solid, like NaCl, and the right side of this equilibrium is going to be the ions, Na+, aqueous, and Cl- aqueous. And so then I can think about an equilibrium constant associated with this, products over reactants. But notice my reactant is always going to be a solid in this context of solubility. So this KEQ here, we will actually call a KSP, solubility product constant. But it works the same way as other Ks we've discussed, like acid dissociation constants or equilibrium constants. And it's still going to be written as products over reactants, but the reactants here are always going to be solid, so you're not really going to ever have a denominator down here in your KSP. So this is an example KSP for sodium chloride. We can write more complicated KSPs, maybe for an equation like this, barium sulfate breaks into barium 2+, sulfate 2-. Our KSP would be barium 2+ times SO4 2-. Maybe consider barium phosphate. Well, now maybe we're just asked to write KSP based on the solubility of barium phosphate. We have to consider, okay, what does this barium phosphate break apart into? Well, it breaks apart into 3 barium 2+ and 2 phosphates. And so now that I have this reaction, I can write products over reactants, and I would get barium 2+ to the 3rd power and phosphate to the 2nd power, shown here. So you will have some exponents according to the coefficients here in this balanced solubility reaction here. And the larger this equilibrium constant, this solubility product constant, the more soluble the substance is, right? The larger this K, the more ions there are, the more products there are. Hence, the more will fit in a given solution. So that's the notion of KSP. And this, like all of our Ks, is unitless. Right? Just like our acid dissociation constants, our equilibrium constants, our solubility product constants have no units. Even though it looks like they should have some molarities here, the value of KSP does not. And this KSP is not solubility. It is the solubility product constant. Remember, solubility does have units of grams per liter or moles per liter. Right? So there are many ways to characterize the amount that will dissolve and the amount of ions you will have in said solution. One is KSP, the solubility product constant. That is different than solubility, which is typically grams per liter, or molar solubility, which is moles per liter. And all of those are just representations about the amount of dissolved substance in an aqueous solution. And so you will have to convert back and forth between these various units. And that's what I'm showing down here. Sort of a shorthand for how I get back and forth between KSP, molar solubility, and mass solubility, or really when we just refer to solubility, it's usually mass solubility. How we will go about that is we can move from KSP to the actual concentration of ions, right? Using the formula for a KSP. This is equating some value of equilibrium product constant or solubility product constant to the concentration of ions. So we move back and forth between KSP and the molar concentration of ions, thinking about it as an equilibrium reaction and doing an ice chart. Hooray. Now, we can then use the equilibrium concentration of ions to figure out molar solubility based on the ratio in stoichiometry of ions to the parent solid. For example, barium is in a 3-to-1 ratio. Phosphate is in a 2-to-1 ratio. So we will use that ratio to get from the concentration of the ions at equilibrium in our ice chart back to a value of molar solubility. And then we can get to mass solubility by just using the formula weight of that compound, barium sulfate, sodium chloride, whatever it is. So this is better learned through doing practice problems. So let's first show you how to get from a KSP into a molar solubility. And so these KSP problems will require us to start the way we have started really all equilibrium problems. Write a reaction for what is happening, write an expression of K, and as we will have to do here, do an ice chart. Okay, so let's just approach this the way we've been doing all equilibrium problems. Let's consider what is the reaction here. Well, it's not a typical reaction where we're adding two things together. We're just writing a reaction based on the solubility. This thing is dissolving, generating ions. It's an ionic compound. So here, for this calcium fluoride, it's a solid on the left. That's the way these reactions will always look. Calcium fluoride as a solid, what is it going to generate? Well, it's going to make 1 calcium 2+ and 2 F- ions. I can also write then an expression for K, products over reactants, as Ca2+ concentration times F- concentration squared because of this 2. Right, so we're still writing our K's the same way based on the reaction we've written. And we're given the value of K here. So now the next step is to think about an ice chart. And for these ice charts, they are always going to look the same way because the reaction always looks the same way with respect to a solid being on the left and the ions being on the right. And we know that for ice charts, we ignore solids, so we are just like never worried about the left side of this ice chart in these solubility product constant problems. And we're thinking about this as if we're dumping calcium fluoride into water, and that's sort of like the start. So like initially there's not calcium or fluoride around. We dump some solid in. How much of the ions do we make? Well, I don't know, but we can say calcium is going to go up by some amount because it's starting at 0. And fluoride is going to go up by some amount. We'll call it 2x compared to the 1x we used for calcium, such that at equilibrium, calcium is x and fluoride is 2x. And now I can plug these in to my expression for K, set it equal to my value of K, and solve for x, which will tell me something about the concentration of these ions at equilibrium. So I just have that shown a little neater here. Here's the ice chart. Left side is nothing. Right side starts at 0, goes up by some amount dictated by stoichiometry, 2x for fluoride, 1x for calcium, such that at equilibrium we have x and 2x. And now I plug these equilibrium concentrations in. So for calcium it is x, for fluoride it is 2x, and my expression for K here shows that it's squared for fluoride. And so 2x squared is 4x squared. And then I have this other x out front. So this really becomes 4x cubed. Right? So now I have 3.9 times 10 to the negative 11 is 4x to the third power. And I can solve for x by dividing both sides by 4 to get 9.75 times 10 to the negative 12 equals x cubed. And now I can solve for x by, well, it's not a square root because it's not x squared, it's a cube root. So look for the cube root button on your calculator. Do that here. The cube root of 9.75 times 10 to the negative 12 gives me 2.1 times 10 to the negative 4. That is equal to x. And the unit here is concentration. It's molarity. So my x here is 2.1 times 10 to the negative 4. Now, you have been trained to solve for x and then consider what does that x represent. When we did a lot of acid-base type of equilibrium, sometimes the x was hydrogen plus and we could get to pH, or sometimes it was OH minus, sometimes it was neither. So let's consider what x represents and how we're going to turn that into the molar solubility of the entire compound calcium fluoride. So this is the last tricky part at the end. This x represents calcium 2 plus. So this is the calcium 2 plus concentration. But we can turn this into a molar solubility expression for the solid by considering the stoichiometric ratio or coefficients before these two species. So this is a 1-to-1 ratio. So here the X amount, which is calcium 2 plus, is going to represent the molar solubility 1-to-1 ratio here of calcium fluoride. So here when we've solved for X, that in our ice chart represents calcium 2 plus, but because it's 1 calcium 2 plus from stoichiometry for every 1 calcium fluoride molecule, then that calcium 2 plus concentration is the molar solubility. If it was a 1-to-2 ratio, then we need to multiply by 2. If it was a 2-to-1 ratio, then we'd have to divide X by 2. But a lot of times it's going to be a 1-to-1 ratio, and so our X here will just represent our molar solubility of calcium fluoride. So that's what the question was after, and we're done. If instead it was asking for the solubility or mass solubility, we would have one final step here to take this molar solubility, moles per liter, of calcium fluoride and turn it into a mass solubility by using the molar mass. So calcium being 40, fluorine being 19, molecular weight here is 78.08 grams per mole. So if it had asked for a mass solubility, you just use that formula weight to get to the mass solubility, right? So that's that last step here in my graph. But we didn't really have to do that for this one. We were just getting to molar solubility and could stop here. Okay, so that's one complete walkthrough of going from KSP to molar solubility or mass solubility. Let's try another practice problem where here we're given something about solubility or concentration of ions and have to work back to KSP. So please pause the video here and try it yourself. And if you don't know exactly how to solve it, at least try to write the reaction represented here, write an expression for KSP in terms of products over reactants, and try to start filling out an ice chart for the reaction. Okay, so it's always a good idea to just think about writing a reaction for what's taking place here. So silver chromate Ag2CrO4 is a solid, double arrow. It's going to break apart into 2 silvers, aqueous, and 1 CrO4, 2 minus, aqueous. Write a reaction, write an ice chart. Left side of the reaction in that ice chart is a solid, so we don't need to keep track of it. We can also write an expression based on that reaction for KSP. It's going to be the silver plus at equilibrium, right? Whatever value we end up getting down here, times, or squared, times the CrO4 2 minus concentration at equilibrium. So silver plus squared times CrO4 2 minus. And now let's see what else we're given in the problem. We've added this solid to water, stirred it, it's gotten to equilibrium, hence this equilibrium arrow. And we check and see that the equilibrium concentration of silver is this. Okay. Now, we started at 0, but we're told this extra piece of information, equilibrium silver. So equilibrium silver is 0.00013 molar, right? So this change had to be going up by that amount. The chromate, though, this 2-to-1 ratio, this chromate went up by half that amount, since the stoichiometric ratio here is 2-to-1, right? This is like calling the change 2x for silver and just x for chromium, right? So we can calculate how much CrO4 2 minus went up. It's 0.00013 divided by 2. And so at equilibrium, the chromate is 0.00065, half of the amount that silver went up. And so these are the equilibrium concentrations we're just going to plug into KSP. 0.00013 for silver, that gets squared. 0.00065 for CrO4 2 minus. And you just multiply that out to get our expression for KSP, or our value for KSP, 1.1 times 10 to the negative 12. And it's normal to have KSPs here that are pretty small. 10 to the negative 8, 10 to the negative 11, 10 to the negative 12. You'll even see 10 to the negative 20, 10 to the negative 30, things of that nature. Okay, so that's this practice problem where we started with some concentration of ions, did a nice chart, and worked back to be able to calculate KSP. Let's try one more here. And feel free to pause the video here and attempt this yourself to try to get all the way from a mass solubility all the way over to KSP. So it's going to be somewhat similar to what we just did, but maybe a couple extra steps here. Okay, let's start it the same way. Think about the reaction, SRF2, that's a solid. What is it going to generate in terms of ions? Well, strontium 2 plus and 2 F minuses. Might as well make an ice chart. I know it's coming. Okay, and I can know that strontium is going to be 2 plus and fluoride's going to be F minus. There's a 2 out front. They're both starting at 0. Strontium goes up by some amount x. Fluoride goes up by some amount 2x. So this is how it's going to look at equilibrium. I also could think about the expression for KSP. Well, that's going to be the concentration of SR2 plus and the concentration of F minus at equilibrium squared. That's my expression for KSP. All right, this last bit of information, or this only bit of information number given in the problem, is a mass solubility. All right, so we're told here that this mass of SRF2 dissolves in 1 liter of water. Oh, sorry, 100 milliliters of water. Okay, so this, suppose I can transition it into grams per liter, like this. 0.011 grams divided by 0.1 liters tells me it's 0.11 grams per liter. And now before I equate any of this to values in a nice chart, which are molarity, I need to get from this grams per liter into a moles per liter. So probably a good idea to use the molar mass here and convert this into a molar solubility. Hence, this first part of this figure up here, go from mass solubility to molar solubility. So, strontium fluoride, the formula weight is 125.62. So 0.11 divided by 125.62 gives me 8.76 times 10 to the negative 4 moles per liter. That is the molar solubility of SRF2. Now, we have the molar solubility, and we can use the empirical formula, but really this should just say stoichiometric ratio or stoichiometry, to figure out what the concentration at equilibrium of the ions must be. So, similar to the last step of this first example, we had a molar solubility, right? And we were relating it to, we had a concentration of ion and was relating it to a molar solubility. We this time have the molar solubility and need to turn it into a concentration of ion. So we're still going to use this stoichiometric ratio, okay? This moles per liter of strontium fluoride, well, there is one strontium fluoride that generates one strontium. So this moles per liter solubility also represents the concentration of strontium at equilibrium. And because there's a 1-to-2 ratio between strontium fluoride and the fluoride ion, then twice this number will be the fluoride concentration at equilibrium. Okay, so we're using the mass solubility, converting it into a molar solubility, then figuring out the stoichiometric ratio to come up with these equilibrium amounts that now can go into my expression for KSP. Multiplying all that out, I get 2.7 times 10 to the negative 9. Okay, so hopefully that's enough practice problems to be able to go any which way from one of these units to another. Remember, all of these are representations of how much ions are going to be floating around in a solution, and you have to be able to go back and forth between them like we've shown thus far. There's one final concept I want to cover in this video, which is much more applicable to everyday life, where maybe there's not 0 strontium, or maybe there's not 0 fluoride, because we tend to be concerned with, the human body or the ocean or some, substance where there's multiple dissolved things around. So it might not be that there's 0 fluoride floating around. So you can have situations where there's going to be some other ion in common floating around, which we've covered previously when it came to aqueous equilibrium as the common ion effect. So we'll now apply this to solubility. We can think about the solubility of calcium fluoride, an example we covered earlier, in a reaction like this. Right? But consider that, well, maybe you're worried about adding calcium fluoride not to pure water, but to some, calcium sulfate solution, where there's going to then be calciums already floating around. How much calcium fluoride will fit now? Will it be more or less? Well, think about this in context of Le Chatelier's. Usually, calcium fluoride is going to dissolve and generate calcium 2+. But if we already have some calcium 2+, it's going to be able to fit less. In other words, Le Chatelier's would say adding calcium 2+ is going to cause a shift back to the left, meaning not as much calcium fluoride will be dissolving into the solution. So if one of the ions on the right side of your reaction here is already dissolved in the solution, then the solubility of this salt will decrease. So if either calcium or fluoride is already in the solution, then calcium fluoride will be less soluble in that solution. Remember, what we've talked about so far in this video is just like pure water, the salt, the ionic compound is dissolving in it. But there might be more complicated solutions, like calcium fluoride in a 0.010 molar solution of calcium nitrate. How much calcium fluoride fits now? We're just following the same format we've been doing with the one wrinkle of changing the initial concentration of that common ion in our ice chart. So we have the same reaction. We have the same expression for KSP, only now the initial calcium is not 0. It is dictated by the concentration given in the problem. There's also 0.010 moles per liter of calcium floating around. Do pay attention to the stoichiometry here, right? This is a concentration of calcium nitrate, but stoichiometry dictates that will also be the concentration of the calcium ion, because one molecule of calcium nitrate makes one calcium 2+ ion. If the common ion here was nitrate, this 0.01 would generate 0.02 moles per liter of nitrate. So when you're coming up with what to put here for this common ion, make sure you do pay attention to the stoichiometry here and figure out, okay, the molarity of the solution, where this common ion is located, what is the stoichiometric ratio between that molecule of calcium nitrate and the ion of calcium? It's 1-to-1, right? Because a single calcium nitrate will make a single calcium 2+. Yeah, it'll make 2 nitrates, but nitrate is not going to affect the solubility here because it's not calcium nitrate, it's calcium fluoride. The common ion here is calcium. So this initial concentration of calcium is 0.01. The initial amount of fluoride is still 0. We're not getting new fluoride ions from anywhere else. And we're still going to have an increase. The left side is still a solid, so still nothing. We're still going to have an increase of these ions on the right. Some will still dissolve, and the F- will go up by 2x, dictated by stoichiometry, and the calcium will go up by x. But now at equilibrium, the calcium will be that initial plus the change, and fluoride will still be initial 0 plus the change of 2x. So now we're just plugging these numbers in instead of just x and 2x. It's 0.010 plus x for calcium, and it's 2x for fluoride squared. And now I'm going to allow for a neglect x assumption. Usually these solubility concentrations are small, even more so in the common ion situation. So this x is going to be something really tiny and going to be safe to neglect. So neglecting that makes this problem fairly straightforward. Now this turns into 0.010 times 4x squared. And you should be able to work through and solve here for x. You can check that it's going to be less than 5% of the thing you neglected it with. It still passes that test. But the x here will be 3.1 times 10 to the negative 5. Now, let's look back and think about what that x represents. Well, 0.01 plus x represents the calcium concentration at equilibrium. 2x represents the fluoride, but we want the molar solubility of calcium fluoride. And what I suggest here is to figure out what the not common ion concentration is at equilibrium. So here, fluoride. And then use stoichiometry to move that back to the molar solubility of calcium fluoride. So here, the fluoride concentration is 2x. So 6.2 times 10 to the negative 5. And I can lastly think about what is the ratio of fluorides to parent calcium fluorides. Well, there's a 2-to-1 ratio here. So I have to divide this equilibrium amount by 2. to get the molar solubility of calcium fluoride. So it really just takes that 2x and turns it back into an x again. Okay. But that's how I would suggest doing it, just for completeness sake. Sometimes students try to put it back here and then use the ratio and get confused. So I recommend at the end using this x to figure out what is the non-common ion equilibrium concentration, and then turn that back into the parent molar solubility based on the stoichiometric ratio. Okay, so the final answer here should be 3.1 times 10 to the negative 5 for the molar solubility of calcium fluoride. We can compare that to the original greater value of 2.1 when there was not a common ion around. So indeed, once we have a common ion around, the solubility went down, as Le Chatelier would suggest. So that'll do it for this lecture. Next time, we're going to think about how pH will affect solubility. And it's similar of just a common ion and there being an OH minus in common or an H plus in common. But we'll solve problems like that and get ice charts involved once again. So that'll do it for this lecture. See you next time.